We're going to talk about the difference between mathematical conjectures and theorems. A lot of people don't know what they are, nor do they understand the difference between them. So the word theorem is telling you that you have something that is proven always to be true. So it always works in math, and the key here is that it has a proof. Now, what's an example of this? Simple. The Pythagorean theorem. Pythagoras said a squared plus b squared is always equal to c squared when you have a triangle that looks like this, and the length A is the bottom, length B is the vertical side, and length C is the diagonal side. If you have a triangle of this nature, Pythagoras said, take this side's length, the bottom side, square it, add the vertical side's length squared, and you'll end up with the length of the diagonal piece squared. But this is only valid for triangles with a 90-degree angle in one of the parts. So we have to have what's called a right triangle for the Pythagorean theorem to work. Theorems always work as long as their requirements are met. So for Pythagoras, if you've got this kind of a triangle, this will always work because it's proven to be true mathematically. How does that differ or get distinguished from a conjecture? Conjectures, on the other hand, have no proof for all cases. But at the same time, they also have no counterexample. So that's the major difference. What would be a nice example of something like this is Goldbach's conjecture. Goldbach's conjecture says this: if you pick an even number, you can find two prime numbers that would add up to create that even number. So let's think about this for just a moment. Prime numbers. What are those prime numbers again? Man, we always forget. Prime numbers are numbers that are divisible only by themselves. Some people say and by 1. They're usually always odd numbers, and the number 1 is not the first one, and that's due to something called canonical form. It turns out the first prime number is 2. It's the only even prime number because any other even number is divisible by that. The next prime number is 3. After that is 5, 7. 9 is not in the list because 9's divisible by 3. You could divide 9 by 3. The next number you can't divide by anything except itself is 11, 13. 15's not on the list. You could divide it by 5 or 3. So you'd hop over to 17, and this will keep on going. All right, what did Goldbach say? He said, you go pick an even number. We can find 2 of these prime numbers. We only need 2. Add them together, and we'll make the even number. What's an example? Well, if you took the number, for example, 12, can we find 2 prime numbers to add up to the even number 12? And it just so happens we've got them on the list. Yeah, if you took 5 and you took the 7, here you go, 2 prime numbers that add up to the even number 12. How many numbers has this worked for? How many even numbers have had 2 prime numbers that'll do this? So far, we've tested it for all the even numbers well into the millions and beyond, and we've never yet found a counterexample. Every even number we've tried, we've been able to find 2 prime numbers that'll add up to create it. However, at the same time, we've never found a formal proof that shows every even number is guaranteed to have 2 prime numbers that add up together. Since there's no formal proof that this will work guaranteeably for all of them, it's not a theorem. But because we've found no even number that has a counterexample, it's a conjecture and hasn't been proven false. So hope this gives you a little bit of an insight between the difference between a mathematical theorem and a mathematical conjecture. See you next time here on the Math Informant. You guys have a great day. Bye-bye.